Today I discuss the kinetic energy of a rigid body with one point fix theorem. Now see here. Find the kinetic energy of a rigid body rotating about a fixed point of the body when the moment and product of inertia of the body relative to the set of axes through the fixed point are known. Proof. Consider a rigid body composed of n particles having masses mi and rotating with instantaneous angular velocity w. If one of the points of the rigid body is fixed, then the translational motion is absent and the body rotates about an axis passes through the fixed point. If vi is the linear momentum velocity of the ith particle and position vector ri with respect to the fixed point, then we know it is given by vi is equal to w cross ri. We know that the kinetic energy of the body is given by T is equal to 1 by 2 summation of mi vi square. Using equation 1, we write 2 as T is equal to 1 by 2 mi vi w cross ri. On using the vector quantity a bar dot b bar cross c bar is equal to b bar cross b bar dot c bar cross a bar. We write the expression for the kinetic energy as T is equal to 1 by 2 mi wi ri cross w vi is equal to 1 by 2 w ri multiply mi vi is equal to 1 by 2 m ri cross vi. T is equal to 1 by 2 w into L, where L is equal to summation of ri cross pi is the total angular momentum. Now to express the kinetic energy in terms of the moment of inertia and product of inertia, we know the angular momentum of the rigid body is given by L is equal to I bar W, where I bar is the moment of inertia tensor and is given by dl I bar is equal to Ixx, Ixy, Ixz, Iyx, Iyy, Iyz, Izx, Izy, Izz. Hence equation 3 becomes T is equal to 1 by 2 W into I bar W if the components of the angular velocity omega and the angular momentum vector the L are W is equal to Iwx plus Jwy plus Kwz, L is equal to Ilx plus Jly plus Klz. Then we write the equation for as Lx, Ly, Lz is equal to Ixx, Ixy, Ixz, Iyx, Iyy, Iyz, Izx, Izy, Izz, Wx, Wy, Wz, Ilx plus Jly plus Klz is equal to Ixx, Wx plus Ixy, Wy plus Ixz, Wz plus dot. And this gives the body rotate about the z-axis with angular velocity w. We have wz is equal to w, wx is equal to wy is equal to 0. In this case the equation 8 becomes T is equal to 1 by 2 Iw square, where I is the moment of inertia of the body about z-axis. Example, here work example. Prove that the statement that a change in time t delta dt of the components of the vector r bar as seen by an observer in the body system of axis will differ from the corresponding change as seen by an observer in the space system. Solution. Consider two coordinate system S and S dash, where S dash is rotating uniformly with angular velocity omega, and with respect to frames S with same origin. Let S be the space set of axis and S dash be the body set of the axis. Let I, J, K be the unit vectors associated with the coordinate axis of S frame, and I dash, J dash, K dash be the unit vector associated with x dash, y dash, z dash axis of the S dash frame. Consider the position vector r bar of a particle in a rigid body with respect to the body set of axis. It is represented by r bar is equal to I dash x dash plus z dash y dash plus k dash z dash. Clearly such a vector appear constant when measured in the body set of the axis. However, to an observer fixed in space set of axis, the component of the vector will vary in time. Let the components of the vector with respect to the space set of axis is given by r bar is equal to ix plus jy plus kz. The time derivatives of r bar, however, will be the different in the two systems. For the space fixed system S, we have dr by dt is equal to I dx by dt plus z dy by dt plus k dz by dt. Similarly, the time derivatives of the vector r bar defined in S dash with respect to the body set of axis is given by dr by dt at t is equal to body is equal to I dash dx by dt dx dash by dt plus z dash dy dash by dt plus k dash dz by dz dash by dt. However, as body rotates, the unit vectors of the body set of axis will be seen by changing relative to the observer in the space set of axis. Hence, we find the time derivatives of the vector r bar in S dash with respect to the fixed coordinate system as dr by dt is equal to I dash dx dash by dt plus z dash dy dash by dt plus k dash dz by dt plus x dash dt dash by dt plus y dash dz dash by dt plus k dash dk dash by dt, and so on. This complete the problem.